I know some of you have a midterm like later today, right? Yeah, some of you do. Okay, all right. Okay. So if you have questions about that, you're certainly welcome to ask. If we run out of questions, I'm going to start talking about differential equations, which is totally fine. We should. Today's 30th. So find the area between y equal to cosine of x and y equal to sine of 2x on the interval from 0 to 2 pi. Yeah. Oh, yeah, you might want to see the thing. Sorry. Good question. Yeah. You just should just yell at me. If you can't see something, don't wait for me to call on you. Just be like, hey, James, I can't see what you're writing because you didn't turn on the thing. Yeah, sorry about that. There we go. Much better. Cool. What's that? Oh, cool. That's much better as well. Although 2 pi would be interesting. All right. So I would still probably graph it, just to have an idea of what's going on. You probably don't actually have to graph this one. But let's graph it anyways. So cosine of x is your usual. And again, we're only going to pi over 2. So I'm going to graph it just to pi. So there's pi. And I know that cosine of x starts at a height of 1. And then at pi over 2 would be equal to 0. And then at pi would be equal to negative 1. So cosine looks kind of like this. And then the sine function, well, sine of 2x has a period of 0 to pi. So the period for this is 1 pi instead of 2 pi. And so sine usually starts in the middle, and then throughout one period, it goes to the top, then back to the middle, then down to the bottom, then back to the middle. So sine will look kind of like this. You get a full period. So it looks like they are going to cross each other between 0 and pi over 2. At least the way I've drawn it. It seems to be that way. So let's set them equal to each other to figure out where the points of intersection are. And to really do this, we really need a trig identity. There's like no other, well, that's not entirely true. There's not a better way to do it. There are other ways to solve this, but the best way to solve it is to recognize that sine of 2x is equal to 2 times sine of x times cosine of x. So they can bring everything to one side. I'd probably bring everything to the right. So 0 equal to 2 sine of x times cosine of x minus cosine of x. Factor out a cosine of x. You're left with 2 sine of x minus 1. So either you need cosine of x equal to 0, which you're going to get when x is equal to pi over 2 or 3 pi over 2 or 5 pi over 2 or any other odd multiple of pi over 2, but pi over 2 is the only one we care about, which is what we're seeing right there. Good. And then we also want 2 sine of x minus 1 to equal 0. Or in other words, we want sine of x to equal positive 1/2, which we're going to get when x is equal to pi over 6 or 5 pi over 6 or other odd multiples of pi over 6 that are in quadrants 1 or 2. So those are the points of intersection. So it looks like from 0 to pi over 6, cosine is the larger function. And from pi over 6 to pi over 2, sine is the larger function. So to find the area between the two curves, it's going to be the integral from 0 to pi over 6 of the larger minus the smaller, plus the integral from pi over 6 to pi over 2 of the larger minus the smaller, which is in this case sine of 2x minus cosine of x. But yeah, they do cross. So it definitely won't come out right if you just do the integral from 0 to pi over 2 of one of them minus the other one, because then you'll get the net area between them instead of the actual total area between them. That is a trigonometric identity. It's good. It's the double angle identity for sine. For cosine, it's very different. I'll just point out that sine of 2 times theta is 2 times sine theta times cosine theta, whereas cosine of 2 times theta is cosine squared theta minus sine squared theta. But yes, those are trig identities that are well known, and I guess you're expected to know them to be able to do this problem. I don't know how else you would do this problem. That's not entirely, it would know. It's not that I don't know, it'd be much harder to do it a different way. So then the rest of this is not too terrible. We're just going to integrate. The antiderivative cosine is positive sine. The antiderivative sine of 2x is negative cosine of 2x divided by 2. So we're going to get minus a minus, so plus cosine of 2x divided by 2, evaluated from 0 to pi over 6. Same kind of deal here. The antiderivative sine of 2x is negative cosine of 2x divided by 2, and the antiderivative cosine is positive sine from pi over 6 to pi over 2. And while I would love to just squeeze that in there, I really should not. I should just use more room because there's plenty of paper, just trees. I'm just kidding. I'm trying not to kill all the. I'm trying not to use all the paper, but I've got enough paper to spare a little space here. So this is going to end up being sine of pi over 6 plus cosine of 2 times pi over 6 is pi over 3 over 2 minus, then we plug in 0, you get sine of 0 plus cosine of 0 over 2 plus, and then we do it over here, we get negative cosine of 2 times pi over 2 is pi over 2 minus sine of pi over 2 plus, sorry, minus, apologies. Plugging in pi over 6, we're going to get negative cosine of 2 pi over 6, which is pi over 3 over 2 minus sine of pi over 6. And if you didn't know what your trig values were, I guess you could just leave it there. But I think there is an expectation that we know these. Sine of pi over 6 is equal to 1/2. Cosine of pi over 3 is also equal to 1/2. Sine of 0 is 0. Cosine of 0 is 1. And then over here we have cosine of pi is -1. So you have negative 1 over 2. Sine of pi over 2 is 1 minus, and you have negative cosine of pi over 3 is negative 1/2 over 2. Sine of pi over 6 is also 1/2. And then we could simplify. We do have 1/2 plus 1/4 minus 1/2 plus negative 1/2 minus negative 1/4 minus 1/2. Cancel some things. 1/2s cancel. And then sure, you have 1/4 minus 2/4. Minus a minus is plus 1/4 plus 2/4. Those cancel. We end up with 1/2. Kind of terrible. You guys all right?
Oh, yeah.
Okay. So that's that. There's really nothing else to do there. Questions about this? All right. Let's look at the other one on there. Which try to read it. Suppose a solution has concentration C of t at time t with C of 0 equal to 15. Let's write that down. And assume that dc dt is equal to 3 times 25 minus C of t. Okay, so we're definitely getting into differential equations territory here. For t bigger than or equal to 0. So the first question is to find all equilibria. Second question is to solve the differential equation. And the third question is to find the limit as t goes to infinity of C of t. So we should probably talk more about this whole topic than just starting with this exact problem, but it's a good problem. So let's talk about what a differential equation is. What's that?
That's a good place to start.
Yeah. So what is a differential equation? Which we often abbreviate as a diff-EQ. It's an equation typically involving a function and one or more of its derivatives. Actually, you don't even need the function itself. It can be just one of its derivatives. So for example, y prime equal to 2. There's a differential equation. It's got a function and or one or more of its derivatives, and there's an equation. That's kind of it. It's an equation involving a function and one or more of its derivatives. Or you could have something like dy dt equal to 5 times y. There's a function y and one of its derivatives. And then there's also the other variable that's the independent variable t. Or you could have something like f prime of x equal to x squared times f of x. There's a function f of x, at least one of its derivatives, and also the variable x. So those are kind of the components that can occur. The independent variable, usually x or t, although you can use any letter you want. And then usually the function or dependent variable and or one or more of its derivatives. You kind of have to have at least one of the derivatives though. So I should really say at least one of the derivatives and maybe the function itself. You can also have more than the first derivative, right? You could certainly have something like y double prime plus 5y prime plus 6y equal to 0. There's another differential equation because it's a function and at least one of its derivatives. So questions about what we've said so far. Eventually, when we start trying to solve these differential equations, the thing we're going to try to find is the function. So when you're asked to solve a differential equation, you're asked to say, oh, what function y or f of x is going to be the solution to this equation? I'll just point out, because it's an easy thing to point out, that for this example here, a solution is the function y of t equal to e to the 5t. Let's check and see if it's a solution. So to be a solution, it should satisfy this equation, meaning if I take the derivative, it should equal 5 times the original function. Let's check it out. dy dt is equal to the derivative of e to the 5t, which is e to the 5t, times the derivative of 5t, which is 5. And that certainly does look like, let's see, 5 times y is 5 times e to the 5t. Those are the same. So that function, y of t equal e to the 5t, is a solution to this differential equation. More generally, I could have thrown a constant in front of this, and it still would have been the solution, right? If I put a c here, the derivative is c e to the 5t times 5, and if I put a c here, 5 times the function is 5 times c times e to the 5t. So that's the whole family of solutions to this differential equation. Yeah, cool. All right. So let me grab some examples here. Yeah. Don't worry, we will work back around to this question. I just don't want to hit all those things right away because there's a few things to say about a few things here. Oh, yeah, all that kind of stuff. So let's delve a little bit more into what makes a differential equation a differential equation. So classifying differential equations. And there's really kind of, I don't know, there's lots of things to say here. So some examples or some types. You can have a first order differential equation that is linear. So order means the highest derivative that shows up. So order just means you're going to get the first derivative. Linear means the function y or whatever we're calling it. I often default to y, but n of t is also a typical choice. The function is raised to the first power. So an example of this would be something like, sure, dy dt equal to 3y to the first plus t squared. That is a first order linear differential equation. That I said y to the first. I wrote y prime. Apologies. That wasn't meant to be y to the first, but I shouldn't even write the prime there. Sorry about that. That's not there. Pretend like it doesn't exist. First order because I have a first derivative. Linear because I have y to the first. I do not care what's going on with t squared over here. That doesn't affect the orderness or the linearity. T squared is whatever it is, doing its own thing. So the linearity is just based on what's happening with the function y, and the order is based on how many derivatives of y we have. So another example here could be a first order quadratic. something like, I'll use different variables, n prime of t plus 3n squared plus 2n plus 1 equal to 5. It's first order because I still only have a first derivative, but it's quadratic because my function n is what's a quadratic function of n, right? There's the second degree term, there's the first degree term, and so on. One more. A second order linear could look something like d squared y dx squared plus dy dx equal to 7. Equal to 7x. Sure, I guess I should throw a y in there. You don't really have to have a y, but to make it more interesting. Second order because I have a second derivative and no higher derivatives. Linear because, again, the y's, as far as the y itself, not the derivatives of y, the highest power of y is just a linear term. It's y to the first. But even if that y hadn't been there, it'd still be linear in y. Because if you don't have any y's, it's linear. It's just boring. It's 0. Okay. So just some language things, really. Most of the time when we're dealing with differential equations, when we're actually trying to solve them, they'll be first order linear, or they'll be something that's relatively straightforward to deal with. We don't typically deal with any second order things in this class. We might deal with some first order quadratics, but yeah, usually they're not too terrible, but it's good to kind of know what's going on. The other kind of terminology we should talk about, which again, yeah, I don't love all this. This next terminology part, I feel like is not particularly useful, but people like to ask about it, so I should mention it. There are 3 types of differential equations that we usually encounter. Although, again, the thing I'm about to say here doesn't really matter when it comes to solving differential equations. When it comes to solving differential equations, what really matters is, for this class, is it a separable differential equation, meaning we can separate all the input variables from the output variables on either side of an equation, or is it a first order linear differential equation? Those are the only 2 types of differential equations we're going to really talk about solving. These types are not those types. These types are the following. You have autonomous differential equations. What you should think of when you think of that an autonomous differential equation is where you're autonomous of time. The differential equation doesn't care what's going on with time. The time variable doesn't matter. In fact, this differential equation right here is an example of an autonomous differential equation because the derivative doesn't depend on the time variable at all. So something where the independent variable doesn't matter, like, for example, dn dt is just a function of n. It's not a function of t at all. And then on the flip side of that, there's pure time, where the differential equation doesn't depend on the function at all, or the output variable. It depends on the input variable. Something like, so I'm looking over at my notes here. Sure. dy dt equal to 3t. Or kind of the last one I feel like this is kind of a cop-out. Non-autonomous just means you can have kind of whatever. Non-autonomous is you have usually time and your output variable. So it could be something like dy dt equals y times t cubed, for example. That's non-autonomous because you have your derivative depending on both your input and your output. Sometimes on exams, people ask you to say, like, is this equation pure time or autonomous or non-autonomous? But I don't see a lot of value in those questions. So, differential equations. We're going to be really concerned with where we have equilibria, meaning where things aren't changing, meaning where the derivative is equal to 0. So, for example, I should write that down. Sometimes I say things and I feel like I should have written that down. So, equilibria. Where things don't change or aren't changing. In other words, where the derivative or rate of change is 0. For example, let's say we're given, sure, a population is growing according to the differential equation. Oh, what did I forget here? dn dt equal to 1.3 times n times 1 minus n over 200. So I just want to point out what this really means. It means that, for example, if I told you that the population at time, I don't know, 0 was equal to 100. And then I asked, is the population increasing or decreasing? It should be a pretty straightforward calculation to answer that question, because all I'm going to do is I'm going to plug in 100 for n. So at time equal to 0, dn dt should equal 1.3 times n of 0, which is 100, but I'm writing n of 0, times 1 minus n of 0 over 100, which is going to be 1.3 times 100 times 1 minus, oh, sorry, I wrote the 200 down there, apologies, minus 100 over 200. So let me ask you, 1.3 times 100 times 1 minus a half should be negative or positive? Positive. And if the derivative is positive, that means the population is increasing. Our rate of change is positive. So here, dn dt being positive means n of t is increasing at t equal to 0. On the other hand, sure, yeah. Yeah. On the other hand, if I were to say that, sorry, apologies, that n of, say, 7 was equal to 500, well, if I plug that in, then at time equal to 7, notice there's nowhere to plug in time here, which would mean I have what kind of differential equation? Yeah, it's autonomous, right? There's no time in there. It's an autonomous differential equation. So it's kind of weird to pick time points here. I'm just kind of doing it anyway. So if I plug that in, I'm going to get dn dt equal to 1.3 times 500 times 1 minus 500 over 200. And that's going to be negative. The positive times a negative number, which means the population is decreasing. So that means n of t is increasing. And it certainly looks like 200 is kind of the boundary. Right? If the population is less than 200, this number here is going to be negative. Or sorry, positive. So the rate of growth is positive. On the other hand, if my population is larger than 200, then this number is going to be negative and the population is going to decrease. So if I want to find the equilibria, we're just going to set the derivative equal to 0. To set dn dt, which is 1.3 times n times 1 minus n over 200, equal to 0. If you're lucky, it's already factored for you. Totally is. So I'm either going to get n equal to 0 or n equal to 200. There's definitely more to say here. What we really care about is whether or not these equilibria are stable or unstable. What do we mean when we talk about stability? Well, an equilibria is stable. If you move away from it, you get kind of pushed back towards it. So let's look at 200 for a second. I'm going to draw a picture in a minute, but I just want to talk about it for a second. So as I just said, if the population is larger than 200, then the growth rate is going to be positive or negative. Sorry, I'm not very good at hearing. I think you also said negative. So if the population is more than 200, my population is going to decrease back towards 200. If my population is less than 200, then the growth rate is positive, and population is going to increase towards 200. So it looks like 200 is a stable equilibrium because if you move away from it, the model pushes you back towards it. On the other hand, 0 is an unstable equilibrium. If you pick a population that's just a little bit larger than 0, like 3, and you plug in 3 for n, 1.3 times 3 is positive, 1 minus 3 over 200 is also positive, and the positive times the positive is positive. So if your population is 3, the population is going to increase away from 0. So stable equilibria, you move towards. Unstable equilibria, you move away from. Now, you can do this all graphically much more easily than saying all these words, but it's good to think about what the words actually mean. So here's the graphical approach to determining stability. I'll point out my words here imply also that there is a non-graphical approach, which is true. There's a non-graphical way of doing this as well. I think the graphical way is easier though. So graphical approach for determining stability. Stability of equilibrium. So we're going to graph. We're going to pretend like dn dt is some new function. We usually call it g of n, I think. We're going to graph g of n equal to 1.3 times n times 1 minus n over 200. We're not going to graph it very well. We're going to do the bare bonesest graph you can come up with. I really just care about my intercepts. So, and I just found here that n equals 0 makes the whole thing 0. Oh, sorry, this is the n axis. And n equals 200 makes the whole thing 0. And this is my g of n axis, but really g of n is just pretending it's dn dt. And I just really care if the graph is positive or negative. So let's look at my intercepts. I already know that if n is bigger than 200, the whole thing is negative. If n is between 0 and 200, the whole thing is positive. And if n is negative, the whole thing's going to be negative because you have 1.3 times the negative number times the positive number. So it looks vaguely, not vaguely, it is parabolic opening downwards. It looks like that. Okay. So there's my graph. But now is the time for the meaning, because here's what this means. And we've already said all these words, we're just going to say them again. So if n is over here, that means dn dt is negative. But if dn dt is negative, so over here, in fact, let's put this down. So over here, dn dt is negative. That means that n is increasing or decreasing. So that means we draw little arrows that say that n goes this way. Because n is decreasing, and n is the thing that's on the horizontal axis. In a similar way, in here between 0 and 200, my derivative, my y values, well, dn dt is positive, which means that n is increasing. And then lastly, over here to the left, although it kind of seems weird to talk about the population being negative, there are certainly times where it makes sense to think of your input being negative, so let's just go with it. Over here, our dn dt is negative, and so the population would be decreasing. Again, some populations that make sense for. And then you just look and you say, oh, look, the equilibrium where we're pointing towards it is stable. The equilibrium where you're pointing away from it is unstable. That's it. So n equal to 0 is an unstable equilibrium. It's still an equilibrium though, meaning if you started with 0 population, you would stay at 0 population. But as soon as you have just a little bit more than 0, people start making people, animals start making animals, and you get more and more and more and more and more. However, this system, it's an example of logistic growth. This system has a carrying capacity that you can't exceed without consequences. The carrying capacity of this system is 200 deer or whatever we're talking about. 200 is a stable equilibrium, meaning in this case, the ecosystem can't support more than 200 deer. So if we have 250 deer, the population is going to decrease because the rate of change is going to be negative. That's all I have to say there. Really. I mean, there's not more to say other than that's what's happening. So typically, if you graph this thing where you're graphing the rate of change versus the function, if you're going from negative to positive, unstable, you're going from positive to negative, stable. And then just with an eye towards the future, I'll say that that means that if you took the derivative of this function and plugged in this point, you'd have a positive slope. So plugging in this equilibrium to the derivative and getting a positive result means it's unstable. Plugging in this point to a derivative and getting a negative value means it's stable. We'll say that again later on, but I just wanted to kind of give you a heads up as to where we're going to go at some point. All right. Yeah, so let's go back to the question that was asked at the beginning that I took so much time writing down and then totally didn't do it at all. Do I still have space on that first page? Nope, not at all. Okay, where did I even write it down? Yeah, I totally did. Okay, fine. So let's go back to this question over here, which is the following. We have that C of 0 is equal to 15. That's just an initial condition. When you see an initial condition like this, where you're told some function value at some input value, what you should think of is, oh, I'm going to probably have to solve for whatever constants come up in this problem. There's probably going to be like a plus C at the end of this thing, or maybe C is a bad choice here because it's C of 0. But there's probably going to be, you're probably going to integrate at some point and have a plus a constant. And then if you have an initial condition, we usually have to find that constant. And then we have dc dt equal to 3 times 25 minus C of t. For t being bigger than or equal to 0. So part A, find the equilibrium. So we're going to set the derivative equal to 0. So set dc dt equal to, so I'm going to write this slightly differently. I'm going to write it as just 25 minus C. When we're writing differential equations, we often don't write the function as the function of time or x or whatever. We just write it as the name. It's fine either way. You can write it as C of t, you can write it as just C. But I think you can all solve this equation in maybe 5 seconds flat. So the answer is C equals what number? Yeah. So C equals 25 is our only equilibrium. Not that you need to say that, just I'm pointing out there aren't any others. Okay, that's all they asked me to do for the first part. So let's move on to the I can't move on to the second part. Let's talk about if it's stable or not. In fact, why don't you all figure out if it's stable or not? So I want you to graph. So this is part A plus graph n of C equal to 3 times 25 minus C. Where n is a poor choice here. I'm sorry, I did not mean to use letter n. I was thinking g of n, but I meant g of c. Sorry, that's a lowercase g, right? See how it turns into a lowercase g there? Look at that, it's perfect. So graph g of c versus c. It should be a straight line. It doesn't have to look great. You just have to have relatively reasonable intercepts. Okay, I'm going to graph it. I know that my x-intercept or my c-intercept is 25. We just found it. Your x-intercept should always be the equilibrium you just found. And then since it's a straight line, if I plug in 0 for c, my y value or my g of c value is going to be 75. So it looks kind of like this. Oh, I missed. I should have just drawn it first. So there's the point 0, 75, which I don't really care about. Here's the point 25, 0. Someone might ask James, don't you get 15 when you plug in 0? And I'd be like, yeah, that's right. This is not the same function. I'm not graphing C of t. I'm graphing the derivative as a function of the function C. I know it's kind of wonky, but so don't get it mixed up, right? This has nothing to do with what's going on over here. We'll talk about the graph because I think that you asked us to graph it. No, but we're gonna graph it anyway. So then, all right. Think about a stable. I want you all to think about, is this stable or not? Inside your own head for a second. Ask yourself, is it increasing, decreasing, or decreasing, increasing? Okay, let's see some thumbs. I want a thumbs up if you think it's stable, a thumbs down if you think it's unstable. Yeah, I think it's stable too. Let's check though. So if you're in here, the derivative is up here, positive, right? You're getting positive values for your derivative, right? Because your g of c is your dc dt. So dc dt is positive, which means c is increasing. Over here, my derivative is negative, so c is decreasing. So yeah, we're definitely stable because we're pointing at the equilibrium. So c equal to 25 is stable. Great. Okay, now let's look at the next question. Solve the differential equation. Sure. So this actually brings up a whole other topic, which is solving differential equations. Usually, if I'm trying to solve a differential equation, I'm hopeful that it's separable, meaning you can put all of your inputs on one side, all of your outputs on the other side. We'll look at that a little bit more after we're done with this. But here, the way you would separate this, you'd say, okay, I've got dc dt equal to 3 times 25 minus c. If I'm writing my derivative on the left side, which I usually am, I want, in this case, all the c's on the left, all the t's on the right. Or in other words, whichever side the derivative is on, the variable that's on top, all of the variables like that should come to that side. And the variable that's on the bottom, the dt, should end up on the other side. So what I'm going to do is I'm going to multiply both sides by dt and divide both sides by 25 minus c. So now all my c's are on the left, all my t's are on the right. And I don't have dt in the bottom or dc, right? Your d whatever, your differential, should never stay in the bottom. It should always end up not in the denominator. And then we anti-differentiate both sides. So we're going to get the integral of 1 over 25 minus c, which is the negative natural log of the absolute value of 25 minus c, equal to the antiderivative of 3, which is 3t plus, let's not use c since c is the function name. Let's call it any other letter in the alphabet. I like k. So all we did was we took the antiderivative of both sides. You might be wondering, why am I getting a negative here? Because of the negative in front of the c there. If you took the derivative of the natural log of 25 minus c, you would get 1 over 25 minus c times the derivative of 25 minus c, which is negative 1. And I don't have a negative 1 there, so I need a negative 1 there to cancel it out. And then our job is to solve for c. And this is where things might get a little bit dicey, especially given that we have an initial condition here. So let's use a little bit more paper. Here's what we've got. We have that c of 0 equals 15, and we have that the negative natural log of the absolute value of 25 minus c of t equals 3t plus k. So at some point, probably not right this moment, I want to plug in t equal to 0 and c equal to 15 and solve for the constant k. But this is not my moment, because I don't want to have to do the negative of both sides and then e to the whatever of both sides. And right, there's a better time to do this. So part of the difficulty of these kinds of problems is picking the best moment to try and do this, and so you're doing the least amount of work. So here's what I would say. Multiply both sides by -1. If the natural log of the absolute value of 25 minus c of t equal to -3t. I don't need to write minus k. -1 times a constant is still a constant. I'm still going to call it k. If you want this one time, I'll probably do it every time, but I try to only do it one time. I'm going to call this k1, and this is my new constant k2, where k2 is just k1 times -1. But really, you can just call them all usually c or whatever letter you're using. You don't have to like change them every time. So now I'm going to exponentiate both sides. So I'm going to say that e to the this is equal to e to the that. So on the left-hand side, I have the absolute value of 25 minus c of t. On the right-hand side, I have e to the -3t times e to the k2. But you know what e to the k2 is? Another constant. And typically, for whatever reason, I usually call it A. Like capital A is just the choice a lot of people use here. So I'm going to call this capital A. I'm going to hold off for just a second, though, because there's one more thing I like to do to make. So what I really want to do for you all is justify that I didn't need to be writing this absolute value the whole time. That I can just kind of ignore it and things are still going to work out just fine. But I will say that you can totally integrate things where you get like a natural log of an absolute value and totally not write the absolute value, and everything's going to be a-okay. Because here's what's going to happen. I'm going to hold off on this a for just a moment. I'm going to say that, well, if the absolute value of all of this is equal to this thing over here, which is always positive, right? E to the something is always positive. Think about the graph. Then I can say that that means that the insides here are either equal to plus or minus whatever you have over here. And I did switch the order, and that is purposeful. So whatever you have inside this absolute value, it's either the positive of this or the negative of this. So for it to work out. If this is 5 over here, then the insides are either positive 5 or negative 5. Okay, but then here's what we get to say. Plus or minus e to a constant is just a new constant. And I'm going to call that A. And then you can kind of just ignore the whole plus or minus garbage the whole time. So it's totally safe to just ignore this absolute value and say, great, we have 25 minus the function we're trying to solve for equal to a e to the negative 3t. And this would be a great moment to find your constant a. So now is your moment. We're going to plug in t equals 0 and c of 0 equal to 15. So over here, I'm going to have 25 minus 15 equal to a e to the negative 3 times 0. E to the 0 is 1, so you get 10 equal to a. Oh, that was a great moment. Probably the best one we could have picked. So now, going back to everything here, we have that all this is giving us 25 minus c of t equal to 10 e to the negative 3t. And then we can solve for c of t by adding, subtracting, whatever. You're going to get c of t equal to 25 minus 10 e to the negative 3t. So that is the solution to our differential equation. If you were to go back and look at the original differential equation, hold on 1 second, dc dt equal to 3 times 25 minus c of t. If you took the derivative of this and then did 3 times 25 minus that, they should be equal to each other. Excuse me. It's kind of neat. Okay. So, not very much time left. So the last part of this question was to find the limit as t goes to infinity of c of t. Well, we already know the answer to this without even doing any of this work. Let me show you what I mean. So, we were told that c started at what value? 15. So if we start at 15, which is right there, what are we going to get pushed towards? 25. That's the limit. You don't need to solve. So I should say, if you have a single stable equilibrium, you almost never need to solve the differential equation to actually find the limit of the solution. Because we know that as time goes on and on and on and on and on, you're going to get pushed towards that stable equilibrium. No matter if you started at 15 or at 20, 30, sorry. This is a type of question people like to ask, where they don't actually make you solve for it. They just say, okay, here's your differential equation. I'm telling you this is the initial position. And then you have to think about where you're starting versus where your equilibria are. And if you get pushed towards the equilibrium or away from an equilibrium. It's a question that really kind of tests your ability to kind of think about what's happening here. But then we could also graph it. So I'll point out that if you graph this thing, actually without even graphing that, I know that we're going to start at 15. So now I'm plotting time on my horizontal axis and my function on my vertical axis. And I know that 25 is a stable equilibrium, meaning I'm going to get pushed towards 25 as time goes on and on and on. In this particular case, it's going to look something like this. But if I had started above 25, I'd still get pushed towards that horizontal asymptote. Right? If we'd started up here at an initial condition of 30, we would end up doing something like that. But then we could actually use the function we found. Right? I mean, why do it the loose way when you could actually say, well, look, the limit as t goes to infinity of c of t is the limit as t goes to infinity of 25 minus 10 over e to the positive 3t, because why would I write it as e to the negative 3t? And then as t goes to infinity, e to the infinity goes to infinity, 10 over infinity goes to 0. You get 25 minus 0, which is 25. We're not surprised at all, though. We already knew that was going to happen. Cool. All right. There's something else I wanted to say here before I run out of time. Yeah. So, yeah. Let's look at one more example. Sure. So, sorry, brain. I'll just point out. So, one more example of a separable differential equation. So, for example, if we had, say, something like dy dx equal to, sure, y squared times x squared plus x squared, we can see if something is separable if we can write the derivative equal to a product of a function of one variable times a function of the other variable. Basically, we can separate it into two pieces where you have just y's and just x's, or just t's and just n's, or just inputs and just outputs. In this case, even though it might not look like it from the get-go, you can totally factor out an x squared from the right-hand side. And so you have x squared times y squared plus 1. So then you can separate things by bringing the dx over to the right. And you should really just do this in one step, but I'm being, I don't know. And then dividing both sides by the function of y. So we've separated it. Y is on one side, x is on the other side. We don't like to play with each other. And then we integrate both sides if we want to solve it. The antiderivative of y squared, 1 over y squared plus 1 is the arc tangent of y. The antiderivative of x squared is x cubed over 3 plus a constant. And if you want to solve for y, you take the tangent of both sides. So y is equal to the tangent of x cubed over 3 plus c. And then I could have given you initial condition and we could have plugged it in and solved for c. Like I could have said, no, I don't know. Let's talk about that more on Friday. Good luck on your test for those of you that have a test. We'll talk more about differential equations on the next day of class, which is Friday.